Okay, exercise 1005 is about the log laws. So the log laws, they equate to the index laws because, as we've seen, a logarithm is an inverse of an exponential. So where we've got a to the m times a to the n equals a to the m plus n, in an equivalent way, we've got log of x times y is log of x plus log of y. That's the first log law. When we've got division, we subtract the powers. When we have division inside a log, we subtract the logs. Where we have brackets and we multiply the powers, that's quite similar to this law here and is used in the proof, where if you've got log of x to the n kind of can fly down the front. It's pretty cool. And this one, it's a really useful log law, that one. So any power on the x can come down in front. Where we have 1 on a is the same as a to the minus 1. Our log law, when we have a reciprocal, is to put a negative in front and undo the reciprocal. In the same way, really, if this was a on b, this one would be b on a. That's another option. I might just write that off to the side. If we have log of a on b, that's the same as the negative of log of b on a. And lastly, this is the change of base law. Now, this is a really useful law. So if you have base a here, then the change of base, this is base b on each of those, we've got x over a, x over a. So that's a really useful law in terms of it allows you to actually put any logarithm into a calculator to calculate what it equals. So I'm just going to prove each of those log laws. So for this first log law, I'm just going to start by saying to let x equal a to the m and y equals a to the n. Now I'm just going to rewrite each of those in logarithmic form. So I'm going to take log base a of each side. So on the left hand side, I've got log base a of x. And on this side, if I take log base a of that, it's going to undo a to the power and I'm going to get m. For this one, I'm going to take log base a of y, and log base a of a to the n is just n. Okay, so the log base a and a to the power are inverse operations. Okay, so I'm going to use those things. Now, first of all, I'm going to look at what does x times y equal. So I'm going back to this first line, x times y equals a to the m times a to the n. So therefore, x times y is a to the m plus n. Now this final line here, I'm just going to take the log of each side of that. Log base a. So log base a of xy is equal, now log base a of this side, a to the power gets undone, so it's m plus n. And m plus n, of course, if I look at this line here, m is this and n is that. So that's the same as log base a of x plus log base a of y. So that has proven that log law. The proof for this second log law is very, very, very similar. So if x equals a to the m, we know that log base a of x equals m, just like in the first one. And as well, log base a of y equals n, just like in that first one. Now, this time I'm going to look at x over y. So if I divide them, just from this first line, that's a to the m over a to the n. So therefore, x over y equals a to the m minus n from that index law. Take log of each side of this. So log of x on y equals log base a of this thing. Log base a undoes a to the power, so that is m minus n. And back from this line here, we can see that that is the same as log base a of x minus log base a of y. So that's the proof of this log law. Okay, this is one of my favorite ones where the power flies down the front. Let's prove that one. So we're going to let x equal a to the m again. So I'm going to take log base a of each side again. So log base a of x equals m. Log base a undoes the a to the power. Okay, let's use the rule with brackets. So if we've got x to the n, remember x is a to the m. So that's a to the m, all to the power of n, which is equal to a to the m times n. Let's take the log of each side of that. Log base a of x to the n is equal to log base a of this side, so that just equals m times n. Let's just write that in the reverse order, so n times m, which is n times m. M is log base a of x. So log base a of x to the n flew out the front, n times log base a of x. Really fantastic, useful log law. This result is just a direct result of the one above it, where we subtract the powers. So log base a of 1 over x is the same as log base a of 1 minus log base a of x. Now, we saw in the previous exercise that this one here is 0. Remember, you can think of logs as a to the power of what equals 1? A to the power of 0 equals 1. This whole thing equals 0. So 0 minus log base a of x, which equals negative log base a of x. And I might also prove it for the other way around. If I have log, I'm just going to leave the base, it could be any base, of a on b. That's the same as log a minus log b with the same base. That's the same as the negative of, I'm just going to write this one first. Sorry, writing this one first. So log b minus log a, and that's the negative of, I'm going to put this one back into a fraction, log of b over a. So that proves that aspect. Okay, I'm just going to prove now the change of base law. A very, very helpful law, as I mentioned already. So given that y equals log base a of x, if I take a to the power of each side, a to the y is equal to a to the log base a of x. A to the power of log base a undoes each other, they're inverse operations. I'm just left with the x. So that's the line I've already written. Now, looking at this piece, I'm going to take log base b of each side of that. So I've got log base b of a to the y equals log base b of x. Now on this side, I'm going to do that magic, the y flies out the front thing, like we just saw. So log base b a equals log base b x. And now I'm just going to divide each side by log base b of a. So this side will just be y, and this side is log base b of x over log base b of a. Now remember, our y is log base a of x. So log base a of x equals log base b of x over log base b of a. Let's look at how we can use those log laws to evaluate some things. So in this example, you've been given that log base 3 of 5 equals 1.465, which it does to 3 decimal places. And you've also been given that log base 3 of 4 equals 1.262, again, which it does to 3 decimal places. So they have been rounded. Now, when you get a question like this where they are given, you must use those values. You can't just use the change of base law that we just saw to evaluate this. You need to use those values, and you need to show you're working. So the first one is to find log base 3 of 20. So you need to notice that these bases are the same. You need to notice that you've got 5 and 4 and 20 and think, how can I use 5 and 4 to make 20? And that's pretty easy really, because 20 is the same as 5 times 4. Now you can use your log law. So that's the same as log base 3 of 5 plus log base 3 of 4. And we know those values, they were given to us up here. So that's the same as 1.465 plus 1.262. And if I put that in my calculator, or just add it in my head, that is equal to 2.727. Example 2 is log base 3 of 0.8. So the thing to notice here is 0.8 is the same as 4/5. So that's the same as log base 3 of 4 on 5. If you write 0.8 as a fraction, you get 4/5. Now, if you're not so good at converting from decimals to fractions, or you haven't memorized that, you can put 0.8 in your calculator, press equals, and ask it to give it to you as a fraction, and you'll see it is 4/5. Now, our log law is then to subtract. So 4 minus log base 3 of 5, and that's the same as this one minus that one. So 1.262 minus 1.465. I can already see that's going to be a negative answer. I believe that equals negative 0.203. So question C is log base 3 of 125. Now the thing to think about here is that 125 doesn't actually use that 4 at all. It's actually 5 to the power of 3. So that's the same as log base 3 of 5 to the power of 3. Now we can use my favorite law, is that the 3 comes flying down the front. So that's 3 times log base 3 of 5. And we know that log base 3 of 5 is 1.465, and that equals 4.395. And lastly, D is log base 3 of 12. So we need to think, how does that use these? Well, it doesn't use the 5 at all. It does use a 4. So the first thing you might want to think of is log base 3 of 3 times 4. Now, we weren't given 3 originally, but let's just see what that is using our log laws. It's log base 3 of 3 plus log base 3 of 4. Now, log base 3 of 3, remember it's 3 to the power of 1. Log base 3 of 3, they cancel each other out and you're just left with that 1. So that's equal to 1. Log base 3 of 3 equals 1. Plus log base 3 of 4, which is 1.262. So the final answer there is 2.262 when I add those. Okay, let's look at a few more examples. So this one is to simplify log base A of 7 plus log base A of 8 minus log base A of 2. Now, because all of those are the same base, we can just use our log laws to put them back together. So this is the reverse of what we were just doing. So we've got a plus here, so we multiply the 7 times 8. We've got a minus here, so we divide the 2. And that's the same as log base A of 7 times 8 over 2. 8 over 2 is 4. 4 sevens are 28. So it's log base A of 28. And just 2 more on this page. Evaluate log base 12 of 12 to the 7. Look, you can just say, well, log base 12 and 12 to the power of the opposite. That's going to equal 7. But let's just do it using that law where the power flies out the front. So that equals 7 times log base 12 of 12. And just like we had up here where log base 3 of 3 was 1, log base 12 of 12 is also 1. So that's the same as 7 times 1, which equals 7, just as expected. And log base 12 of 1 over 144, I did one like this in the previous exercise. That's log base 12 of 1 over 12 squared. We can use that law that that's the negative of log base 12 of 12 squared. The 2 goes flying out the front. The answer is negative 2. Log base 12 of 12. Inverse operations, they undo each other. The 2 is left alone, negative 2.